Hello everyone, welcome back to another class of digital electronics. We are discussing about this JK flip-flop. So the circuit diagram of JK flip-flop is here. You can see we have two cross-coupled. We have here two cross-coupled that gate 3 and 4 and 1 and 2 is the input. And this is the functional table which we keep discussing, and the characteristic equation of Q3 plus 1 is equal to J Q bar T plus P bar T of T. And we come to know about this reserve condition that when J and K both are 1, the output is complement. Next output is the complement of the present output. And in that, since the propagation delay time taken by to series that gate is delta t. However, Tt is the time for which the circuit is being triggered. So we can see here the kind of toggle things were happening. Now, after that, we come to know how to solve this toggling race around condition in JK flip-flop using master slave JK flip-flop. Then yesterday in our physical mode class, we could learn this excitation table of JK flip-flop and how to design 2-bit synchronous counter. Now, as I have given a task, a kind of say design a 3-bit synchronous counter, that is binary counter using JK flip-flop. So this is the question which we are trying to solve. Let me see what it is. Okay. So step is, first of all, we try to understand what this question is saying. So question is your design a binary counter. So this is a counter which counts up number. So we need 3-bit counter. So what is the counter size? 3-bit here. And type is synchronous. Synchronous here means that the state in each flip-flop or the counter changes simultaneously with respect to the clock pulse. So that is the meaning of synchronous. And we have to make this, or we have to realize this counter with the help of JK flip-flop. That has been also given. So now these are the meaning, these are the things which is given as far as statement of the problem is concerned. Now let us try to realize or solve this problem. So in this solution, first step is the making of state table. So state table of this problem consists of, first is present state of the output, then of course next state of the output, and based on this present state and next state, what shall be the input. Okay. So these are the 3 columns. Now in this further, based on the given specification, we try to put. So present state, that is say Qt, next state is your Qt plus 1, and here we will be having input. So in present state, since it is a 3-bit counter, so we need 3 flip-flop. So suppose flip-flop A, flip-flop B, flip-flop C. So output of these 3 flip-flop is a Qt. So same flip-flop will change its state. That state will be next state. Next state, again I will write here A, B, C, but now it is a Qt plus 1. This QA of T plus 1, QB of T plus 1, or QC T plus 1. This is like that. Okay. Just to simplify, I have written ABC only. And here, so far as inputs are concerned, so with respect to A flip-flop, that is JA, we will have JA as input. So JA, KA, these are the 2 inputs. Similarly, JB and KB and GC and PC. These are the 3 flip-flops of the inputs. So So just try one flip flop. So this is clock. So this is J. This is P. And here say P A and P B. So these are the input. This one and this one. These are the outputs. But only we are considering this one because second one is just complement of first one. So here this will be P A, P B, P C. Because these are the three numbers of JPSF flip flop. So now writing the T1. So click the values. So present state is suppose 0, starting number because this is 3 bit, so 3 bit information. So 0, 0, 1. The next will be after increment it will be 1. The next will be 2. Next will be 3. Next will be 4. Next will be 5. Next will be 6. Next will be 7. So these are the number which are the present state. So now based on this we will fill up the next state. If present state is 0, 0, 0, so next state will be 0, 0, 1 because that number will be 1 after 0. If present state is 0, 0, 1, that is the 1, next state will be 2, that is 0, 1, 0. If present state is 0, 1, 0, that is 2, next state will be 0, 1, 1. If present state is 0, 1, 1, that is 3, next state will be 4, that is 0, 1, 0, 0. If present state is 1, 0, 0, that is 4, next state will be 5, 1, 0, 1. If present state is 5, next state will be 1, 1, 0. If present state is 1, 1, 0, that is 6, next state will be 1, 1, 1. If present state is 1, 1, 1, that is 7, so it will count again from 0. So that is the, this is the present state and next state information given in the state table of 3-bit synchronous counter. Now based on that, we have to find out the inputs of this flip flop. Okay. For that, we need excitation table. Okay. So let me write here excitation table of the flip flop for the reference. So here I write Pt and here Pt plus 1 and here J and T. So 0, 0, 0, 1, 1, 0, 1, 1. So this excitation table of JP flip flop is for 0, 0, it is 0 cross, 0, 1, 1 cross, 1, 0, cross 1, and 1, 1, cross 0. So this is the excitation table of JP flip flop. This we have to refer while filling the input information. So consider these two. This Q A of T and Q T plus P A T plus 1. So these two. Because this is the present address state of the flip flop A. Okay. So take this first case 0, 0. For 0, 0, what is the input of JAK? First one, JAK 0 cross. So we can write here 0 cross. Again 0, 0, 0 cross. Next is 0, 0, so here 0 cross. Next is 0, 1, fourth one. For 0, 1, 1 cross from here. 1 cross. 1, 1. For 1, 1, we can see excitation table gives the value cross 0. So we can write here cross 0. 1, 1 cross 0. 1, 1 cross 0. 1, 0. So 1, 0 is cross 1 of the excitation. So this way we have filled this input value for first flip flop. So 0, 1, total should be 8. 1, 2, 3, 4, 5, 6, 7, 8. So it is okay. Now similarly go for the next second flip flop, that is QB of T with QB T plus 1. So middle line. So we have to consider these two. So 0, 0. So we have to fill up here 0, 0 is 0 cross. Then 0, 1. 0, 1 is cross or what cross? 1 cross. 1, 1. 1, 1 is cross 0. Cross 0. And 1, 0. 1, 0 is cross 1. cross 1. Next is 0, 0. 0, 0 means 0 cross. 0 cross. Next is 0, 1. 0, 1 means 1 cross. 1 cross. Next is 1, 1. 1, 1 is cross 0. Cross 0. Last is 1, 0. 1, 0 means cross 1. Cross 1. So in this way we have filled the input for QB of T and QB of T plus 1 or JB KB. So last one. So last one is the C. So we can change this color. Suppose this is the C, right? And here is QC of T and QC of T plus 1, these two. So 0, 1. For 0, 1, you can see 0, 1 is 1 cross. Then 1, 0. 1, 0 means cross 1. Then again 0, 1. 0, 1 means 1 cross. You can see here, these values are 0, 1, 1, 0, like that only. So if it is 1 cross, cross 1, 1 cross, cross 1, 1 cross, cross 1, 1 cross, cross 1. 1, 2, 3, 4, 5, 6, 7, 8, like that. So these values are like that only 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. So now we have filled the state table of your this 3-bit synchronous counter. So this is the step number 1. So it's required citation table of respective flip-flop to fill up the information regarding the input value. Based on the output, what should be the input? So up to that, I hope you are clear. Next step is to simplify, to find out the expression, Boolean expression for JA and KA, JB, KB, JC, PC, using the Carnot map. Okay. So 3 variable K-map we did here. So next page I will go. Okay. So here, is it any way to copy and paste? I don't know whether it will be the entire thing. Select all, then copy, make a copy of entire thing. I think it will be to make a copy of one only. Okay, no problem. I'm going to make a Carnot map for JA. I want to simplify for JA and for KP. So 3 variable map I will draw here. So here A bar, B bar, C bar, bar C, BC, BC bar. Same goes here also. So this is 0, 1, 2, 3, 4, 5, 6, 7. Same goes here. So now we try to fill up the values. For GA 0, 0, 0, 1. 0, 0, 0, 1. So this is 0, 0, 0, 1. Next is all cross. So all cross you can put cross, 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 cross. Now this is the JE. Now I want to fill up similarly for KE. This cross, 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 cross 0, 0, 0, 1. Cross, 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 cross 0, 0, 0, 1. So this is the information we have filled. Now simplify. So here this is 1 and this is cross, so we can easily make it clear. Yeah, similarly here also. So now JA is equal to, you can see here QB, QC. So we can write in full form now, otherwise BC. The solution is BC. because since it is output, so I've just written down in expanded form. Similarly, for KA is again QB and QC. So sound sensible? Now go for JB. JB and QB. So right here, QB, 1, 2, 3, 1, 2, 3. It will be A bar, A, B bar, C bar, B bar, C, B C, B C bar. Same here. So let us find out the values. You can see here 0, 1, cross, cross. So let me see the code 0, 1, cross, cross. Next is 0, 1, cross, cross. Next is 0, 1, cross, cross. Okay. So 0, 1, cross, cross. This is the J. Now QA is JB. KB, you can see cross, cross, 0, 1. Cross, cross, 0, 1. Cross, cross, 0, 1. Now cross, cross, 0, 1. Cross, cross, 0, 1. So we have filled the information for JP and KB. Now solve it. So we can see we can make a quad group of over if we consider this X as a 1. Similarly here we get quad. So you can see here JB is equal to C. That is the KC. Similarly, KB is equal to KC. This is the now last one you can see here for JC KC there is no 0, only 1 cross, 1 cross, 1 cross, only here cross, 1 cross, 1 cross, 1. So it can be easily made as JC is equal to group of 8 ones, that is the octet. Similarly, KC is equal to 1. So we found this expression. J A is equal to QBQC, K is equal to QBQC, the input for JB is equal to QC, input for KB is equal to QC, and KC is equal to 1. So now let us try to implement. We have already got the inputs of flip-flop. So now realization using the flip-flop. Realization of the circuit of the 3-bit synchronous counter. Using JP flip-flop. So we simply draw 3 flip-flops here. This is supporting APA, APA, ACPC. So support this TA, TA bar. This is TB, 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 TB bar. This is DC, 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 DC bar. Now this is the clock for each. Since it is a synchronous, so all flip-flops are triggered with the common clock. That is why the name is synchronous. So this is CLK clock pulse. Now we already know that GA is equal to QB QC, PA also QB QC, JB is equal to QC, PB equal to PC, JC is equal to what? PC is equal to what? So these are the inputs which we have to get. So JA and KA we join together because both are receiving same input, and add gate of put here gate output of QB and QC. QB is here, just QB, and this is QC. That is what. Next is KB and KB would join together and connect QC. So here to JC and KC would come together with the logic 1. Just give you logic 1 as an input. So input is already corrected. Now I will give the output. So you can correct that one. This is in first. You can say second. Okay, let me put here. Yeah, yeah. The third one is. So this is A, this is B, and this is C. So we just put here LED to observe the output. So first clock pulse comes, suppose first clock pulse comes, it is a trade pulse. First clock pulse one comes, so QA, QB, QC, all will be 0, 0, 0. So first number is 0, 0, 0. So it will be here 0, 0, 0. Next will be 0, 0, 1. Next clock pulse will come this one. So it will be A is equal to 0, B is equal to 0, and C is equal to 1. Second pulse to here. Next clock pulse will come, the next state will be 0, 1, 0. It means that B will be here above. Okay, this will be state 0, and this will be 0. The next will be 0, 1, 1. This B and C will be 1. Okay, this will be 0. Okay. Next is 1, 0, 0. Now the fourth clock pulse 0, this is 0, this is 1, this is 2, this is 3, this is 4. Fourth is come, so QC will be 1, but both are 0. Here, this is 0, this is 0, this is 1. You can see here 0, 0, 0. The next will be 0, 0, 1. Next will be 0, 1, 0. Next will be 0, 1, 1. Next is 1, 0, and so on. You can draw the timing diagram also. So this is the complete circuit diagram of your 3-bit synchronous counter. I hope you could understand. So let us revise it. What was the step? First, in the statement of the problem, from there you have to determine how many flip-flop is required. You have to know citation table of the respective flip-flop, make the state table, project state, next state, and the input of this flip-flop. So fill up this information for project state 0, 0, 0 to 1, 1, 1. Next state from 1, 1, 0, sorry, 1, 0, 0, 1 to 0, 0, 0. You then find out the inputs of all this JK flip-flop using the excitation table. And after that, you simplify, find out the Boolean expression of each inputs of flip-flop. Then based on that, you realize the circuit. Here, so JA, KA is nothing but here QB, QC, which is here JA. And JB is nothing but here QC. And JC and KC equal to logic 1, which we are doing here. But all flip-flops are triggered with that. With this clock pulse, forward clock pulse, that is the synchronous counter. So this counter will count the number from 0, 0, 0 to 5, 6, 7, and repeat. Yeah, lastly, we can make one state diagram basically. State diagram. So state diagram. So these are the 0, first state is 0, 0, 0. Clock pulse count, so this state will be 0, 0, 1. The next state will be 0, 1, 0. Next state will be 0, 1, 1. Next state will be, put the arrows. Next state will be here 1, 0, 0. Next state will be 1, 0, 1. Next state will be 1, 1, 0. Next state will be 1, 1, 1. And repeat it again. So this way, this is the state table. I hope this is simple state table of 3-bit synchronous counter. So let's see the arrow. So this way it is moving. Simple. Thank you so much for attending. See you soon in next class.